Hello, my name is Chris Horn. I'm a software engineer at HPE on the Lustre team. This talk is about troubleshooting LNet multi-rail networks. I'll start by providing a brief overview of the multi-rail feature. Next, we'll cover how to view stats that are made available by LNet and how we can use those stats to validate that multi-rail is behaving correctly. We'll then take a deeper look at the LNet health feature. Historically, LNet only allowed one interface per LNet network. So here we have two physical hosts, and each host has a single interface on the O2IB0 network. Because of the one interface per network limitation, if we want to add additional network capacity, then each additional interface would need to be configured on a different network. So here we've added two additional interfaces to each host and two additional networks, O2IB1 and O2IB2. From LNet's point of view, each NID, which is the A at O2IB0, B at O2IB1, etc., each NID that you see here is treated as a unique peer. LNet did not have any way to correlate additional NIDs with a single peer. So this isn't terribly useful because each interface can only talk to exactly one other interface. So to really leverage all the bandwidth, you need the upper layers to know about all of these NIDs and to try to send traffic to all of them. We could use aliasing to allow the three physical interfaces to all talk to each other, the six physical interfaces to all talk to each other. But the configuration becomes even more complex. And again, there's nothing in LNet that ensures we're going to leverage all of these interfaces intelligently. So we're still relying on upper layers to help drive traffic to each interface and utilize the full network capacity. With that background, in comes the LNet multi-rail feature, which allows multiple interfaces on the same LNet network, and it allows multiple LNet endpoints, or NIDs, to be associated with a single peer. So the complexity of the configuration goes way down, and LNet now has all the information it needs to fully leverage available network capacity. The one thing that is missing is changes to the API to allow users of LNet, namely Lustre, to take advantage of the multi-rail feature. As I said earlier, historically one NID was equivalent to one LNet peer, but now we have multiple NIDs associated with a peer. So we want to give Lustre, or other users of LNet, an easy way to target a peer rather than target a specific endpoint. This is where the concept of the primary NID comes into play. The primary NID is simply a way to uniquely identify a multi-rail peer. The first NID that is configured on a node is designated the primary NID, but it's important to understand that there isn't anything otherwise special about that particular interface. The term primary NID doesn't mean that that interface is special or preferred for traffic. It is simply a convenient way to get a unique identifier for an LNet peer. So you can kind of think of it as being equivalent to a UUID or a hostname or something like that. The primary NID is also used as a key for modifying peer definitions when using the LNetCTL command line interface. This picture illustrates how the local LNet configuration translates into a peer entry. On the left, we see this peer has NIDs A and B at O2IB. The fact that A at O2IB appears first in the output of LNetCTL net show indicates that this was the first NID configured on the node, and it is thus designated the primary NID for that peer. On the right, we can see the corresponding peer entry in the output of LNetCTL peer show, showing the primary NID A at O2IB, as well as the list of all of the NIDs for that peer. This picture illustrates why I want to stress that the primary NID is really just an identifier for an LNet peer. On the left, we have a Lustre client that connects to a Lustre server over the O2IB network. The client also has an interface on a TCP99 network that is used for some other purpose. Because the TCP99 interface was configured first, it is designated the primary NID for the client, and this is reflected in the server's peer table. This may cause some confusion because messages in the server's log file will reference the A at TCP99 NID, such as the message shown at the bottom of the slide. But this doesn't indicate that the server and client are actually communicating on the TCP99 network. The message shown at the bottom of the slide is simply stating that a connection was restored to a Lustre client whose primary NID happened to be A at TCP99. Turning to statistics, the LNet-CTLNet show command exposes stats for local LNet interfaces. Here I'm running the command on a node with two LNet interfaces on the TCP network. The stats are pretty self-explanatory, so the send count is simply the number of messages that have been sent from that local interface, and the receive count is simply the number of messages that were received on that local interface. We can see the stats are all 0, as I've not yet sent or received any LNet traffic. And then I manually discover another multi-rail peer just to set up the next slide. If you don't know anything about discovery, that's fine. It's simply how LNet learns about the LNet configuration of peers that it communicates with. So after running discovery, I run a simple loop to send 50 pings to this peer. The multi-rail selection algorithm will attempt to round robin across all available local interfaces. And the stats show that after the pings, the traffic was split roughly equally between the two local interfaces. So this tells us that multi-rail is behaving as expected. There are analogous stats that track sends and receives to and from peer interfaces. So in this example, I've reloaded the LNet module to reset the stats, run discovery on the same peer, and then the LNet-CTL peer show command displays the send and receive stats for those peer NIs. Again, the send count is just the number of messages that we've sent to that particular NI, and the receive count is the number of messages that we've received from that particular peer NI. I again execute 50 pings in a loop, and we can see the traffic is split equally between the peers NIs as we would expect. I do want to highlight something about this example. So if you look at the loop, the destination NID for the ping is the same for all 50, right? But we're splitting the traffic equally between both endpoints. I mention this because it raises a subtle issue if you're trying to verify that you have connectivity between two peers. The LCTL and LNet-CTL ping commands are not necessarily reliable to accomplish that because of the multi-rail selection algorithm, you don't actually know which source interface and which destination interface the ping is actually sent from. And in fact, if some interfaces are unhealthy, the LNet health feature, which we'll talk about later, will avoid those unhealthy interfaces. So if you're just checking connectivity with ping, it may look like two peers can communicate just fine when in fact some of their interfaces are not communicating properly. So that ties into just a couple tips on validating our live system. Again, the ping commands are not reliable, but I have noted this LU ticket 14939 that proposes an enhancement to the LNet-CTL ping command, which allows you to specify a specific local interface that you want the ping command to be sent out of. And then that will also fix the destination interface so that multi-rail, basically the multi-rail selection algorithm, won't be run there. So you can be sure that the specific local and destination interfaces are what will be used in the ping, and that helps you verify that you have connectivity between all of the available NIs. So otherwise there's no real magic here. Usually we're interested in running a particular workload and seeing how LNet is behaving. So the strategy there is just dump these stats to a file that for the peers and the local interfaces that you're interested in, run your workload, dump the stats again, and then compare them. You can write a script to compute the delta, And then that shows you exactly how the interfaces have been utilized while that workload is running. And similarly, you can watch these stats on a live system in real time. And usually if there's a problem, it's pretty apparent because you'll see the stats incrementing for some subset of your interfaces, but not one of them. And so that kind of indicates that, okay, I need to go look at that particular interface where I'm not seeing those stats increment. So taking a closer look at LNet Health, LNet Health added a new selection criteria to the multi-rail algorithm, namely the health value. And so a health value is assigned to your local NIs as well as peer NIs. So here I'm showing the health values from the point of view of the sender. And let's suppose that a message is sent from NID A to NID Y. And for some reason that send fails. So depending on how the Lustre network driver classified the failure, the sender will decrement the health value of the local NI, the peer NI, or both. In this case, we've decremented both. The NIs then go into a recovery mode where they are pinged at a regular interval. These are LNet level pings. The idea is that a successful ping will increase the health value, and it lets us know that NI is healthy and we can start using it again. So let's say the ping to NID A was successful. Its health value is restored to the maximum, and LNet will start using it just like before. But the recovery ping to NID Y failed, so its health value is still decremented, and LNet will prefer sending future traffic to either NID X or NID Z. So if we think about this situation in terms of the stats that we just talked about, we expect to see the stats for NID B and NID C to be incrementing while NID A is in recovery. And then once NID A recovers, then all three of the local interfaces from the point of view of the sender, those stats will be increasing. And then similarly, the stats for the peer NIs for the receiver, we would expect NID X and NID Z to be incrementing while NID Y is largely static. So in that context, I did just want to mention an outstanding bug, which is that when an interface has been unhealthy for a while and LNet hasn't been using it for any traffic, and then it is restored back to service, LNet will try to balance out the total number of sends across all of the interfaces, and so you actually end up getting more traffic sent to this interface that was just returned to service. It was formerly unhealthy. And so if you're looking at the stats at that point, you might see that, oh, the stats for this interface that just came back, those are increasing quite a lot, but the other interfaces are not increasing as much or at all. And so it may look like you have a problem, but actually everything is okay. And once the counts are roughly balanced again, then you start to see that regular round robin behavior. So again, this is a bug, LU13575. By the time this video is posted, there should be a patch available for that. A little bit more on LNet Health. So again, it adds health as an interface selection criteria. It's actually the most important selection criteria. So it's the first thing that LNet considers when determining which local interface or remote interface to send a message from and to. And so if an interface is unhealthy, it's going to be avoided unless all the interfaces are unhealthy, in which case, we're going to prefer the most healthy interface for sends. Send failures are categorized by the Lustre network drivers as either a remote failure or a local failure. And then there's a third category, which is basically the Lustre network driver doesn't know if the problem is on the local side or the remote side. So in that case, we decrement the health value of both the local interface and the remote interface. And the reason the Lustre network driver is responsible for this is that the driver is the one that has the information about why a particular send failed, right? So if if the O2IB Lustre network driver was unable to establish a connection to a remote peer, that's one kind of failure, versus it already had a connection, it sent the message, but then it hit a timeout, right? So depending on how exactly a message fails, it can get categorized in these different ways. Some errors will trigger an automatic resend at the LNet layer. And the idea here is that LNet can quickly try a different path in the network to deliver that message successfully, and thus avoid bubbling up errors to the upper layer, namely Lustre, in which case, that causes Lustre to go into its RPC, portal RPC recovery mechanisms, maybe reestablishing a connection, those sorts of things. But there is a trade-off here, because the longer that LNet holds onto a message, that delays propagating errors to the upper layer. So, for example, if we know that a message cannot get delivered to its destination, it's almost always better to just tell Lustre right away, we can't deliver this message, so you need to, engage your recovery mechanisms and try and recover from that. But in the cases where we can deliver it, it's better to not give those kind of false errors to Lustre. So there's a bit of a trade-off here between this feature and notifying Lustre of network errors. Another feature of LNet Health is response tracking. So an LNet put message can have an ACK requested. So when the put is delivered, the recipient sends an ACK back to the message originator. And then every LNet get message, there's a reply response to that. So what response tracking does is just try to make sure that the ACKs and the get replies are received in a timely manner. And if they're not, the idea is we kind of catch the failure sooner, rather than the alternative being, we're waiting for the Lustre portal RPC timeouts, which would be a longer amount of time. So we can detect error conditions sooner, inform the upper layers, inform Lustre, and they can engage their recovery mechanisms. Again, interfaces that are involved in send failures go into recovery, where they're pinged, and then once their health reaches back to maximum, then they're kind of returned back to full service. So I wanted to dive a little bit deeper into LNet Health. I mentioned how the Lustre network driver is responsible for classifying send failures. So I wanted to provide a little bit of visibility into what that looks like, how you can see what those classifications are. So the way to do that is to enable this net tracing in the Lustre debug log. So that's that first command, lctl sepparam debug equals plus net. And then I send a ping and then dump the Lustre debug log to a file. And what we're looking for is this LNet health check routine. And so we can see here the ping was successful. So the LND said, hey, the get and the reply was A-OK. Everything is working normally. And here's a failure case. So here we hit a local timeout sending this ping. And so this would indicate probably a problem with the local interface. And the use case, the reason you might want to look at this is kind of twofold. One is, when a system is under load, it can be kind of hard to tell where exactly a problem is if you're having communication errors. And so, you might see, okay, I've got some local interfaces on this node that are not healthy. I've got some remote interfaces that are not healthy. What really is going on here? What kind of errors am I seeing? And so you can enable this tracing, check the LNet health check. You'll see these local timeouts. You'll see remote timeouts, remote errors, different things like that. And that just kind of gives you a clue of where you might want to look for where the problem is. And the other thing here is that there have been some bugs where the Lustre network driver is misclassifying errors. So if you know that there's a problem with, say, a remote interface, but the health value for that interface isn't getting decremented, or you see LNet, keep trying to use it. You can enable this tracing, check the log, and you might see like, oh, well, all of these are getting classified as local issues. So that's a bug. File a ticket, let us know, we'll get it fixed up. So before I wrap up, I always want to give a shout out to Olaf and Amir. When talking about multi-rail, Olaf presented the original proposal for the LNet multi-rail feature at LAD in 2015, and Olaf and Amir designed, implemented, and tested the vast majority of this multi-rail feature set. So big thanks and shout out to those two. And lastly, I just wanted to list these tickets that I mentioned or kind of alluded to. So those may be of interest to you. Thank you for watching my presentation, and I really hope to see you all in person at LAD in 2022.